Hi, everybody. I'm going to make a few videos today that will be a substitute for our normal Wednesday class because this time change on top of everything else just feels a little bit aggressive. So I want to finish up some of the stuff from chapter 8 that we were talking about. And in particular, I want to go back to the idea of an irreducible polynomial. And that'll wrap up this video. The next video that I make will start in on chapter 9. So here we go. Okay, so last class we talked a little bit about the polynomial long division and how we might use that to find GCDs. I thought I would define the GCD for us. So this is all still in chapter 8, which is about polynomial rings. And if we take a field and we look at the polynomial ring, f bracket x, and we take f, g, and d to be elements of f bracket x. Let's say they're all non-zero. Then d is going to be the GCD, the greatest common divisor of f and g. And we're going to denote that the same way we would for the integers with the notation GCD of f and g, provided a few things happen. And it's going to be really similar to what we had in the integers. First of all, we want to make sure that d is monic, meaning that the leading coefficient, whatever it is a 1. Which means that d looks like x to the n plus an minus 1, x to the n minus 1 plus blah, blah, blah. That first term, an, is guaranteed to be 1 in a monic polynomial. We also want to make sure that it's a common divisor. So d divides f and d divides g, but that's our notation for d divides f and d divides g. That means that we have a common divisor. The first part is going to guarantee that it's unique for us. So if by insisting that the first coefficient is 1, there's only going to be one possible GCD. It's kind of like insisting in the integers that the GCD is positive. And finally, we want to make sure that if h is in f bracket x and h divides f and h divides g, so we have another common divisor, then h should also divide the greatest common divisor. So our greatest common divisor polynomial is big enough that any other divisor of f and g will also have to divide it. And so that is where we get the greatest piece. I would encourage you to look back at this definition for the integers and compare these two. They look really, really, really similar. In fact, a good time to do that would be before midterm 2. When this will be fair game. So just a word to the wise, this would be a good time to come back and look at it. And then the theorem, which we actually did talk about last time, it's theorem 8.7 in our book, is that if the GCD of, if d is equal to the GCD of f and g, then there exist polynomials m and n in f bracket x, where d equals fm plus gn. And that's exactly like what happens for the integers. And it's the same thing. In the course notes that I'll post about this stuff on Blackboard, in fact, it's the day 17-18 notes, there's an example if you wanted to work through an example by hand and see how this works. So we've got the polynomial long division that we can do to calculate GCDs and then to write GCDs as linear combinations. You can find that file on Blackboard, on Overleaf, if you want to actually go through and let LaTeX do your long division for you. Totally fair game. The other thing that is interesting is talking about irreducibility, which is a parallel discussion to prime in the integers. So as a reminder, and we talked about this in both classes last time, the definition of irreducible is that So again, F is a field. F in F bracket X of degree at least 1. So no constant polynomials here, 0 or not, degree at least 1, is irreducible provided for all H and G in F bracket X, where F is H times G. So when I can factor it as H times G, either the degree of H is 0, in which case the degree of G is the degree of F, and we could show even more, actually. In fact, if the degree of H is 0, that means we just factored out a constant. So that means G is a constant multiple of F and vice versa. Because that H, its degree is 0, which means it's a non-zero constant polynomial. So we could multiply by H inverse, and that would be just fine. So either the degree of H is 0, and then the degree of G is the degree of F, and even more, the G and F are multiples of one another, or the degree of G is 0, and then the parenthetical above applies to H. Right, so then H is a multiple of F and F is a multiple of H. So this is saying any way you try to factor this polynomial, the only thing you can do is pull out a constant. You can't actually divide by a more interesting polynomial and get a nice clean division. So we can think a little bit about when something is irreducible. This is proposition 8.12, which is a proposition we're going to use a lot in this class. We're going to use it over and over and over again. So I'm going to put it in a blue box here because it's super important. Several years ago, a class of students named this proposition. I said, wouldn't it be nice if this proposition had a name? And they said, sure, we're going to call it Pete. I was thinking more like the, roots of small degrees or polynomials of small degrees theorem, but no, they named it Pete, and Pete stuck. So I'm going to call this Pete. If you can think of a nice acronym for what Pete might stand for, polynomials, ETE, something like that, that would be great. What the proposition tells us is that let's let F be a field, and let's let P be an element of F of X. So we've got some polynomial in F of X. Then we can conclude some things. Firstly, if the degree of P is 1, then P is irreducible over F. And in fact, I want to amend my definition up above a little bit. When I said that this is irreducible, the field here matters. I want to say over F. And at the end of this proposition, Pete, I will give you an example of why F matters. So let's insert that into the definition, and then we'll do an example to show why I went back and put that in there. Okay, so if the degree is 1, then the only way this thing can factor into 2 factors is those factors have to have degrees that add up to 1. That's what we know about polynomial multiplication. And the only degrees I have for polynomials that are going to add up to 1 are degree 0 and degree 1, which forces one of the degrees to be 0, any which way I factor this thing, which means it's going to be irreducible over F. So degree 1 polynomial, cool, automatically irreducible. The second thing is that if the degree of P is in the set 2, 3, so I have a degree 2 or a degree 3 polynomial, that implies that P is reducible over F if and only if P of A is equal to 0 for some A in F. And I want to talk about what that means. I want to sketch the idea of why that's the case. So 1 is the case because there just aren't enough degrees for anything interesting to factor. I can't pull out something of degree 1 without the other thing having degree 0. And I can't pull something of degree 2 out of something with degree 1 if I'm only allowed to have non-negative integer powers, which is how polynomials work. So the idea, the sketchy idea behind part 2 is I'll do it for degree 3, and you'll see that it'll work out similarly for degree 2. So let's say the degree of P is equal to 3. That means that, so if P is reducible, actually, P is reducible if and only if there exist G and H, neither of which have degree 0. Or negative infinity, because we can't divide by the 0 polynomial, for which P equals G times H. And that means that, so that can happen. In order for that to happen, we need that the degree of P has to be the degree of G plus the degree of H. And the only way that I can add up to 3 without using 0 and 3 is to use 1 and 2. So without loss of generality, the degree of G is 2 and the degree of H is 1. Oops, sorry, I didn't mean to do that. So then what does it mean for the degree of H to be 1? Means that H looks like something times a constant polynomial x minus a, where a is an f. And that's true if and only if h of a is equal to 0, because I plug that in and I get 0. And that's true if and only if then that p of a is also equal to 0, because h is a factor. So for degree 2 and degree 3, there's no way to reduce this thing without getting a degree 1 factor. And we've seen that those degree 1 factors lead to roots. Now, what goes wrong if the degree is 4? If the degree of P is equal to 4, we could have something like P is equal to x squared plus 1, x squared plus 1. In q bracket x, and that doesn't have any roots in the rational numbers, right? The roots of this thing are plus or minus I, and each one has, multiplicity too. So this is reducible. P is reducible. By definition, P has degree 4 and also has 2 degree 2 factors, which means we can reduce it. I built it as a reducible polynomial by making it the product of 2 things, but it doesn't have any roots over Q. Now here's where the over Q part matters. The fact that I'm paying attention to what field this is, if I had replaced this with, let's say, C, if I put this in C bracket X, I can reduce it even further, and it does have roots in C. So x squared plus 1 is irreducible over Q. I can't factor it any further over Q, but x squared plus 1 is reducible over the complex numbers, or if you like, Q, where we throw in I and then all the other things we need to make that into a field, because x squared plus 1 equals x plus I times x minus I. Now we needed to get a bigger field so that we could reduce it all the way down to degree 1 factors, but the fundamental theorem of algebra says over the complex numbers, any polynomial is going to reduce down to things with degree 1 factors. So there really are no irreducible polynomials of degree greater than 1 over the complex numbers. It's really working over the real numbers or the rational numbers where we have irreducibles of higher degree. And we're going to look at some theorems later on. I think it's chapter 10 and 11, where we start talking about some more ways to check that things are irreducible. But Pete is a great one. Pete says if your degree is small, like 1, 2, or 3, it's quick to check if you're irreducible. The rational roots theorem that you looked at on the homework might be another way to decide if something is reducible or not. And we'll touch on that again later in class. So that, my friends, is the wrap up of chapter 8 here. There is a slightly more expanded version of the notes that I've put on Blackboard where you can see some more examples and things. I think it's nice to work through them by hand. As always, please bring questions about those to office hours. And I'm going to stop recording now.